What's going on, everybody? It's been a while, but I had something interesting come up, kind of in a, let's say, work-related thing, programming-related thing. Um, Made me go down a rabbit hole involving Go, Elixir, and benchmarking a specific thing that I thought was too slow. And I was right. It was too slow. It was about 3,500 times too slow. And this wasn't like a Go is faster than Elixir thing. I think those types of benchmarks are kind of silly. Um, this is more like I wonder if my intuition about the fact that I'm using the wrong data structure for this is true, and using benchmarks to kind of confirm that, and then also confirm a solution. So I took, I'll walk you through the details in this video, but I took a kind of like standard Go implementation. I'm a decent Go programmer. That's what I do in my day job, and I'm a fledgling Elixir programmer. But I like Elixir, and I'm trying to learn it, and I'm kind of an Elixir noob. And I was kind of doing this problem, and my intuition was like, I think based on how Elixir implements this, this is going to be really slow. And I was right, and by picking the right, or kind of getting to the right data structure, I sped it up several thousand times. I think in the end, the Elixir solution is like 3 to 5 times maybe. Sorry, I should say Go is still 3 to 5 times faster than the Elixir solution. But I'm using Elixir, and I get to use Elixir and all the wonderful things that gives me. So I just thought this might be interesting. And I guess, again, I'm less concerned with like the specific numbers. It's more about like the approach. And I wanted to share that because I used to be kind of, I don't know, like benchmarking. It all seemed very like complicated and scientific. And then like every time you see a benchmark article, there's 20,000 comments on like, well, you idiot, you benchmarked the wrong thing. And benchmarking well, I think, is hard, and that this is not an attempt to do that. But this is like benchmarking as part of my engineering process, and as part of trying to get to the root of like why something I'm doing is wrong, and then also having metrics to back up that, hey, I took a wrong thing and made it right based on my intuition, and then the actual hard numbers that benchmarking gives me. So let's jump in. Just before we start, I've open sourced this, so like pretty much everything I do. It is open source, and you can kind of, I put the whole read up in there, and I kind of cleaned up the repo, and you have an Elixir and a Go directory with those, the sort of same function in both of those applications, in both of those programming languages. So check that out if you'd like. All right, so let's start with the Go version. I think it's likely that more of you are familiar with Go than with Elixir. So let's just kind of step through the kind of problem I was doing. This is, again, it's kind of abstracted to not, to not be work or the specific project I was working on. But basically, it is the same problem as if you wanted to choose a random word from say a list of words that is, the size of like a language, maybe like 20, 30, 50,000 words in that list. And it's sort of each, I say list here, we're talking about like a dynamic array, right? Like there would be a Python list, like a Go slice. You have a list of words, and you keep wanting to take a random one up to some number. Say we want, this is like Diceware passwords, right? You want a password kind of string that is like 5 to 6 words long. And that's a fairly secure password if you can really choose them randomly. So to build a string like that, we have a word list. So that's like kind of our dictionary, you might call it. I guess it's not really a dictionary because it's not like keys and values, but you know what I'm saying here. It's words, English words in this case. You have some number of them that you want, like I said, 5 or 6. Like how long do you want the word string to be? How many words should it consist of? There's one kind of little hitch in that in this application, there could be no duplicates. So like two people can't have the same password. It's not really passwords, but you know what I'm saying here. So there's like a map of taken or really a list of taken word strings that we can't have a duplicate of, okay? So the Go implementation is very straightforward, I would say. Totally straightforward, procedural kind of programming code. We're going to have some chosen words that we're going to build up. You can see it starts as an empty string slice in Go. And then words, which will kind of get reused in each iteration as we go through. The for loop, this is an infinite loop in Go. So this is like a while true, basically. So let's loop until we break out of this with a return here, right? So on each iteration, we're going through the length that we want. We pick a random index inside of that kind of space of our word list, all the words we can choose from, and then we pick a random word at that index from that word list and append it to our chosen words, right? And we do that length times, and then we know that we have a chosen words string slice that is length long. Okay. Then we join those together with a hyphen character. We check to see if it's a duplicate by looking in our taken list. This is just, again, a small complexity introduced by the kind of like specific use case I was using this for. And if it's not a duplicate, we just return the words, we're good. If we have, I have a log statement here because it would have been low probability but kind of dangerous if we had a duplicate. You 5 or 6 words, that's to the power, so like size of the word list to the power of 5 or 6 are the odds, I think. I'm not a mathematician, but so it'd be weird if you had like 25,000 to the 6th and you found a duplicate in any like human time scale, not doing this, millions of times a second. So I would log that, and then there's nothing else. We would just start at the loop again, right? So if we had a dupe, it would log and do this whole thing over. Cool. Really straightforward kind of code. We're just like, length times, we're going in, picking a random, and you could even like optimize this, right? Like, it doesn't matter. So this is a fairly straightforward implementation. And likewise, I'm not going to focus on this too much, but this is not the part I'm doing many times. So like, I don't care if this is a couple nanoseconds slower than some other way of doing it. It's like, I'm just building a word list from that, from an actual like text file once. So I'm loading that, and then I have that word list in memory. It's a string slice, right? Pointer to a string slice. Cool. So that is the Go implementation. Let's look at what that looks like in Elixir, or at least what it looked like in my first approach. So you don't have to be super familiar with Elixir, but Elixir does things it's a functional programming language. So like the functional way of doing things is going to be what you see. And it looks a little bit different. It is tail call optimized, so you'll see a lot of recursion getting used, that kind of thing. But it's just, I wouldn't focus too much on the syntax. This is not like a Learn Elixir video. I'm also the wrong person to teach that at this point. I haven't used it for nearly long enough and for enough stuff to be any kind of expert on it. So basically in Elixir, you can define multiple functions with the same name in a module that depending on the guards or whatever, like they'll be called, or depending on the arguments, they'll be called in certain cases. It's a nice way if you're writing recursive code to have what would be like your like exit condition or your 0 condition be actually a separate function clause. It makes everything really nice and keeps like extra kind of control flow out of your functions. It does this with pattern matching and all kinds of like really, really cool features. You should look at Elixir. It's a cool language. Anyway, so I have basically, here's the main function. This is doing kind of the same, so these two functions are doing kind of the same stuff that you saw Go doing. you can see my first attempt is like much more procedural, and then I was like, oh, like that is just not how Elixir and like variables work in Elixir. So I left it in here just as a like funny place that I learned a lesson and did something kind of like wrong. So you can see we've defined a choose words function that basically this is our exit case. If we have 0 words left to choose, then just our words accumulator is what we return. If you don't know what an accumulator is, it's just a thing that you use to kind of store state on the stack as you kind of, is it called iterating? Yeah, like recursively iterate. I mean, it's still iterating. You're just doing it recursively with an additional function calls. And then you pass an ever growing, in this case, list of words down that stack, or kind of distributed across all those stack frames, and then that's what gets returned. It's sort of, as the recursive functions kind of zip back up, the list is returned. This sounds really freaky, but it's just how functional programming kind of does this, and it is kind of freaky. That's why I like functional programming. So choose words takes a word list. Kind of remember that from Go. A number of words, that was the length in Go, and words that we already have. That's the accumulator. That's what we're adding to each function call. And then the definition of this function is it literally just calls itself, and with the same word list, of course, with one less word, because we're doing an iteration right now, so we have to do one less next time. And then this words accumulator is itself with one extra word tacked onto the front of it. So the first element is getting added each time. That's just the most efficient way to add an element in the front of the list, is what you can very efficiently access in Elixir. Cool. And again, this is like loads something in from a file. We're not super worried about benchmarking that because it happens once. So that's choose words. That's how we get the words. And obviously chosen words, we basically just we do that, we join them with a hyphen, and then we just check if they are a member, if they exist in that list of taken or map of taken words. And if it's not a duplicate, we just return that. That's good. And if they are a duplicate, we just recursively call ourselves the same new function. And we just try again. Cool. So now you've gotten a little taste of, like, I guess, the functional style of doing this. Again, not a huge expert, but this is a fairly straightforward thing. And let's look at the benchmark. All right, so let's benchmark this ourselves, starting with Go. Not because Go is better, not because Go is faster, although it is very likely faster because it's statically typed and compiled and highly optimized. If you're doing this the first time, you might have to download the dependencies. I trust that you can figure that out yourselves. And then we're going to run go test bench. And I'll show you the, while it does that, it's going to do that. It's benchmarking, it's benchmarking, it's benchmarking, and I'll just very quickly show you the, so we're on the scale of like nanoseconds per op, and what I'm also looking for here is like, is this scaling linearly, or did I have like an O of n squared, oopsie. Basically is, you know, this is about 10 times as many words, so I'm benchmarking 5 words, then I'm benchmarking 55 words. I don't know why I picked lots of 5s. I thought 5s were funny that day. But you know, is this on the order of 10 times as long? Yeah. Is this on the order of 100 times? Yeah. On the order of. So that feels like linear growth to me, and that like satisfies one of my intuitions about this, so that's good. Let's look at main tests. This is fairly straightforward. They're all basically the same call. I'm doing if you've never done benchmarking in Go, it's super easy, super fun. You might know testing T for your tests. Well, this is testing B for benchmarks. You start each function name with benchmark, and then whatever it's benchmarking. You do your setup, whatever you need to do. Like this takes some time. Making an empty map takes some time. Okay, it's malloc. I don't know. And then you reset the benchmarking timer. And then here's the benchmarking loop. This is like the classic Go benchmarking loop. This, we're going to do it b.n times, however many the benchmarking code thinks we need to do this. And we're just calling literally that function we defined and went over before. So this is build random word string. We can go to the definition of that, and that is what we were looking at before. Oh, it's funny. I have an actual comment related to the real app that this was on. Again, this is not. It's like an app I was building for myself. Now let's look at the Elixir benchmarking stuff. And in the README, I have like how to do these benchmarks. So you can run it yourself. You can see like you go to the Elixir directory, mix steps get to install dependencies. You would also need Elixir installed, obviously. Jump into an Elixir shell, and then run the benchmarking like function in that module. So let's do that. Elixir, get in there, and then bench. We're using benchy for benchmarking, and then we'll just say run. You can leave off. It's kind of cool. You can leave off. It's so you can tell Ruby people worked on Elixir because it has little syntactic sugar or niceties, like you can leave off parens off of a function call if that function takes no. If you're not passing arguments, if that function takes no parameters. And this is going to go ahead and benchmark a bunch of stuff. Let's look at that code real quick while that's running. And at the top, this is my original attempt. That just has everything, and I split it out into their own functions so you can see stats a little nicer. Oh yeah, and this is the old and busted. This is the original. I was just like Googling Elixir benchmarking, like how to, and there's eprof, which is the built-in like Erlang profiler, which actually is quite nice. But then I found this Benchy library, and it just looked nice, and I used it, and it was nice. So run basically just runs these three test cases. Again, basically the same thing with slightly different numbers in the function call. And then I'm basically building up a word list and an optimized word list. You'll have to ignore those results for now. And then the comparing this. So before I show you the results, you can see I'm comparing a slow version and a fast version here, both in Elixir. And what I saw when, I'll just show you the first result. Close your eyes, everyone. Close your eyes. Close your eyes. We have the Go results up there, and let's just say 5 words. So you just ignore the array one. So on average, we're taking 2 milliseconds to pick 5 words. Indeed. We are taking 22 milliseconds to pick 55 words. Hold on to your butts. 5 words is 2 full seconds. It's 2,000 milliseconds. That's like 2, is it billion or? I think it's 2 billion nanoseconds. Anyway, it's just insanely slow compared to this, right? So 5 words at 218 nanoseconds. Well, now it is 10,000 times slower. It is 2 milliseconds. And that is the point at which I was like, what the fuck is going on? I'm doing something terribly wrong. And I looked, I'll show you in the code actually, I had an intuition about why this was happening. And I even wrote this as a comment. I was like, I think I read somewhere that Elixir lists are this thing called cons cells, which are sort of like a recursive data structure. Very elegant. If you get a little bit hot and bothered when you think about like Lisp and that type of thing, it's like real sexy. And that is not a criticism at all. I'm one of those people. But it's stupidly slow when you are not dealing with the first element. The first element is the only fast one to append, to pop, to access, to modify, because you have to do a linear search. So like linear time, right? Like a list with n elements can take you up to n times to fetch an element from. If that nth element is at the end, well, then you've just visited every single one before getting there. A programming language with dynamic arrays, and by the way, this includes Erlang, so you can use the Erlang arrays module to do this, I found out. But a programming language like Go, like in main, the way that it accesses like a slice, right, which is essentially a dynamic list, is this: you have constant time access to every index. So the 0th index through the n minus 1th, I guess the nth index, you essentially have constant time access because Go can just look at like a memory offset, basically, more or less. They're dynamic arrays, so they're a little more complex, but I think amortized, you still get like linear time. So every one of these slices like has a length field somewhere. So that is like a constant time lookup. I know exactly how long it costs me, like one, not CPU cycle, but a constant time lookup for how long a list is. I pick a random index from 0 to that number, and then I access that in constant time. And I can access any, the first index or the last one in sort of the same amount of time. It's the same. It's just a different memory location. And those, thanks to RAM and the RAM model, that is equally fast, regardless of where that is in memory. So that is not the case with these Elixir lists. And so I went looking for a dynamic array. What I ended up landing on, to keep this video from getting too long, you can read the whole thing that I kind of went through before. What I landed on was an optimized version, random words array. So this is the exact same program. Simply, when we build this word list, there may be a more efficient way of doing this, but again, I don't care about this part. We create a new array, and we use the Aya vector implementation to do that. So this is like a dynamic, think of it as a dynamic array. And then you do get constant time lookups. Now, there is a thing you can do in Elixir, and you could make your own data structure, right? You could make a map where where the keys are like indexes from 0 to n, and the values are then the actual like list element you would have in the Elixir list. And then you can get performance that I think is close to this. I don't think it's exactly this fast, but it would be close, and it'd be a hell of a lot simpler, and you wouldn't need a package for it. So like that's one way to fix the data structure. But I was down a rabbit hole, so I kept going. And from there, the implementation is essentially the same, except now I can have this rand from array function. And so this is really the only new part. Because I have an array where I can just access indexes, and I have a constant time size lookup, so the arrays have a size function in that module where I can just pass in the array and constant time get the size of that array, the number of elements in it. I subtract 1 to get the last index, zero-based indexing. Then I access that index. That's what I return. The last value in one of these Elixir functions is what it evaluates to. So this last line is essentially what's returned, is what you'd say in another language. So that's the only change. So now it's working on arrays, or really on these vectors. And the random lookup should be much faster. That's really all that's changed, is that random lookup. Instead of scanning up to that random index each time, is essentially constant time. So that thing I'm doing over and over, that thing has become fast now, on the same order of fast as Go compared to how it was before. So these will have finished. Let's look at it. You can say the original, you can see the original implementation was, like we said, 10,000 times slower. The new one is just significantly faster. So incredibly much faster. I have done the math for you just to verify this in another tab, but this is 580 nanoseconds for the 5 words. So we've, it's just so unbelievably much faster. It's funny. So it's, yeah, sure. Like it's half as fast, I guess, as Go, but being half as fast as Go is pretty damn good. Like that's, I mean, the deviation is actually super high for this one. So let's look at the a better kind of sample size and stuff here. Looks like it's scaled pretty much linearly. Again, it's like 10 times that number. We're doing essentially 10 times the words. I just made this hard by picking 5s. I don't know why I did that. And then again, 100 times, and that is, God, let me convert this for you. It's 580,000 nanoseconds, and let's see where that puts us with Go. 580,000 nanoseconds. Yeah, so kind of like just like call it 3 times-ish, a little less than 3 times faster Go. But that's, see, like that I can buy. That I can buy easily, that Go is 3 times faster, kind of on just like this type of stuff than Elixir. And that's like a price I'm happy to pay with Elixir for the increased expressiveness and just kind of the fun of using that language. It has that good feeling. I mean, if you look at the Stack Overflow survey every year, people fucking love using Elixir. Like people that use it love it. It's got a sort of like Ruby-like feeling. Like the language is nice to you. Like it wants you to feel good, and the tooling feels good, and the error messages look good and feel good, and it's a great language. And that's like, I will happily pay that penalty, but I will not happily pay it is 10,000 times slower penalty, where small operations take seconds to complete. That's just like, but again, like my intuition was like, that's not, the language is so much slower, shruggy emoji. It was like, this is the wrong data structure, because that's not language differences. That's like, there's a major implementation difference that is leading to astronomically slower performance. So yeah, I don't know if this is helpful to anyone, or at least interesting. I hope it was. But just wanted to kind of share my my intuition and how I kind of follow that, even in a language I don't understand. I'm not an expert in, and I've never benchmarked stuff in it before. But don't be afraid of this stuff. I think rabbit holes are the best learning opportunities often, and getting too much in your own head about like, oh, is this useful? Do I need this for work? Like I didn't need to do this, but I enjoyed doing this, and I learned a lot from doing this. And benchmarking in Elixir, I'd never done that. It seemed kind of hard to me when I started, and like everything else, it's a couple of Google searches and a couple hours of your time playing around with it away from being something that isn't scary at all and is totally understandable and maybe even enjoyable. I keep saying enjoyable about benchmarking, dude. I think I need to start worrying about myself a little bit. For anyone that's still here, leave a comment and tell me you're still here at the end. You stayed with me. One thing I'm thinking of doing, and definitely leave me feedback in the comments if you're interested in this, but I'm thinking of doing short project-based videos, series on YouTube or courses that are just programming projects, and like simple but realistic projects. There's so much like leak code stuff on YouTube, and I think it's been covered really well, and I'm not particularly an expert in that either. So, but one thing I am good at is getting stuff done, building real stuff for people, and I like doing it. And so I thought we could do a couple of toy projects on the channel for anyone that is like trying to learn Go, especially, or Elixir, you know, what I'm learning, or whatever else I'm working on. I was thinking of a project like maybe a link shortener, maybe an kind of like a random anonymous email inbox generator. There's like those privacy email things, you know, it's like sign up with like a sort of email inbox that you can then just like instantaneously delete again once you get the free ebook or whatever it is. Yeah, I don't know, projects like that, I think that's what you really learn programming through, not by watching videos on programming languages or like even reading books about a programming language, I think they're only useful, at least to me, when I'm reading them next to building a real project that's not like the tutorial or like whatever abstract programming concepts the book is talking about. I just want to see like real code, building a real thing. And if you want to see that too, let me know in the comments below. Anyway, thanks for watching, and I will see you all in the next one. Peace.